this is the DTFT transform pair number 7. Transform pair number 7. It is an important result. It is a result that requires us to go through systematically to obtain, and we will do this in the following form. It says, the property says, if x of n is equal to r raised to the power n sin omega p n plus 1 divided by sin omega p. Notice, it is an exponential weighted sequence. It is a sinusoidal function. Omega p is the frequency. The numerator term is a sinusoid. The denominator term, is it a sinusoid? No, because there is no n term there. It is only a scale factor. So, again it is there as a, it looks like a complicated function, but it is actually sin omega p n plus 1, that is a sinusoid, which is scaled by an exponential scaling function r power n and a constant scaling function 1 over sin omega p, and this is multiplied by u of n. That means only for the positive side. Okay. Now, why is this necessary? If you go back and look at the Fourier transform pair, let me just pull up that that chart. Fourier transform theorems. I need the Fourier transform pairs. Where is that? 6, 7, 8, 9, 10, 11, 12, 13. Okay. We are given r is less than 1. That means as you go towards plus infinity, r power n is a decaying function. But on the other side, for n less than 0, you will find that this is an expanding function or a growing exponential. So, therefore, to constrain it to a sequence that is bounded, we have u of n. Okay. So, it is an exponentially weighted sinusoid. The exponential weighting function is a decaying function and a scale factor 1 over sin omega p. Now, this has got a DTFT given by the expression on the right hand side. Okay, this has got a DTFT given by 1 over 1 minus 2r cosine omega p e power minus j omega plus r squared e power minus j2 omega. Okay, so when most people look at this transform pair, they say, well, this is too complex, I do not know even how to start. Not to worry, we will go step by step. Okay, we will call this as x e of j omega, and we will call this as form 1, the first form of the DTFT. As I mentioned, we will start with a couple of steps which will help us simplify this particular problem. The step 1 is a result from general algebra. Okay, general result from algebra. Again, very simple result, but something that you must be familiar with. Now, if p of x is a polynomial of order n, is a polynomial in x of order n. Okay, that means it is a polynomial of order n, highest power of x that is there is n, and it has real coefficients. With real coefficients. I think now this is a standard result from general algebra. How many roots will it have? The roots of p of x, there will be a total of n roots. A polynomial of order n, there will be n roots. Let us name them as p1, p2 up to pn. Okay. Now, the important result that we have is that pi where I equal to 1 through n, these are the roots. they will either be real valued, because the polynomial has got real coefficients, real valued, or they will occur as a complex conjugate pair. They will occur as a complex conjugate pair. What do we mean by that? If I write down the factored form of p of x, I will get some number of real roots. I is equal to 1 through n1 x minus pi. These are real valued roots. Then come the complex roots, j equal to 1 through n2 x minus pj x minus pj conjugate. Okay? And the condition is that n1 plus 2 n2, each complex conjugate pair contributes 2 roots, n1 is the real roots, the total must be equal to n. This is what the factored form will look like. So, this is a product, a set of first order terms multiplied by a set of second order terms. Second order terms have got complex conjugate roots. This is always true. Now, I want you to look at what does this complex conjugate pair look like. X minus pj, so this is step 2. For step 1, we said, okay, this is how the polynomials will get factorized. X minus pj, x minus pj conjugate. Please multiply and tell me what you are getting. You will get x squared minus 2 times the real part of pj, because you get pj plus pj conjugate times x plus mod of pj whole squared, because pj times pj conjugate will be mod pj squared. Okay. Now, step 3. You now have the result from step 1 and step 2. I would like you to apply it to the following polynomial multiplication. 1 minus r e power j omega p e power minus j omega multiplied by 1 minus r e power minus j omega p e power minus j omega. Okay, I am going to ask you to label this as p or pj, this as x, this as pj conjugate, and this as x. Okay. Now, if you go ahead and use the form that you have in step 2, what you will get is 1 plus, sorry, it will be 1 minus 2r e power j omega p plus e power minus j omega p, that will become cosine omega p e power minus j omega plus r squared e power minus j2 omega. Okay. I will just give you a moment. We used a general result from algebra, which says that you will either get real, if a polynomial has got real roots, you will either get real roots or you will get complex conjugate roots. I am interested in the complex conjugate pair. If I multiply the complex conjugate pair, notice that I will get real coefficients, a polynomial with real coefficients, second order polynomial. Now, I am using that to this result to simplify the expression that we have. Now, compare equation number 1 and equation number 2. Okay. So, what we now have is that x e of j omega can be written in multiplied form or it can be written in factored form. Okay. So, that is step 1. So, here it is, x e of j omega can be written as 1 minus 2r cosine omega p e power minus j omega plus r squared e power minus j2 omega. This we said was form 1. Okay. we can show just now through the factorization that this can also be written as, okay, help me with this, 1 minus r e power j omega p e power minus j omega, 1 minus r e power minus j omega p e power minus j omega. This is form 2. They are identically equal. We have just written it down in factored form. Okay, I hope you are comfortable with that. Now, step 4. Step 4. Step 4 says apply partial fraction expansion. Partial fraction expansion. Now, this is something that you would have studied in the study of series expressions that you have obtained to form 2. Okay. So, what is partial fraction expansion? If I were to write it in the form of polynomials. So, if I have a polynomial of the form 1 minus x minus p1 into x minus p2, I can write it as a divided by x minus p1 plus b divided by x minus p2. This is partial fraction expansion, PFE. Okay, so apply it to form 2. So, applying this to form 2, we can say that xe of j omega can also be written as a divided by the first factor 1 minus r e power j omega p e power minus j omega plus b, a second term which is given by 1 minus r e power minus j omega p e power minus j omega. Okay, whatever was the two roots, they are going to be part of the partial fraction expansion, except that rather than a product of the two roots, we are now going to have it as individual rational functions which are scaled by different constants a and b. Okay. Now, the last step is to obtain a and b. Obtain a and b. Okay. How do we obtain a and b? We take this, call this as equation 3, multiply 3, both LHS and RHS by 1 minus r e power j omega p e power minus j omega. What will you get? Use x e of j omega form 2. Use x e of j omega form 2. Okay, so, the left hand side, if you multiply with 1 minus r e power j omega, you will get 1 divided by 1 minus r e power minus j omega p e power minus j omega. This is equal to a times b into 1 minus r e of j omega p e power minus j omega divided by 1 minus r e power minus j omega p e power minus j omega. Okay, I have done a cross multiplication, I have obtained this result. Okay. Now, if I can somehow set this term to 0, equal to 0, then I will get an expression for a. So, how do I set this term to 0? The numerator has to go to 0. The numerator has to go to 0 means 1 minus r e power j omega p e power minus j omega equal to 0. This implies e power minus j omega is equal to 1 over r e power j omega p. if I substitute e power minus j omega in this expression, I will get it. So, once I substitute, I will get a, you have to substitute this condition on both left hand side and right hand side, and you will get the expression that a is equal to 1 over 1 minus e power minus j 2 omega p. Okay. Now, let me just don't worry about the steps or just follow the sequence and make sure that you don't make any errors in the substitutions. Okay. What did we do so far? We took the expression on the right hand side, which we called it as form 1, and then we factored it, wrote it as 2 factors. We call that as form 2. Then we wrote it as partial fraction expansion, that is form 3. Now, once you have obtained it in the form of a partial fraction expansion, we have to get a and b, the 2 coefficients, and the steps that we got, we showed for a, we got the expression for a. So, let us just complete that. So, we got the expression for a as 1 over 1 minus e power minus j 2 omega p. Okay. You can simplify it in the following manner. You factor out e power minus j omega p. What you will get is e power j omega p minus e power minus j omega p. Okay. You can see that this is of the form of a sine function. So, if you simplify, this will become 2j sine omega p. Can take the other e power j omega p to the numerator. So, what you will get is e power j omega p divided by 2j sine omega p. This is the value of a. Okay. Similarly, following the same steps, but now with the b term, please verify that you get b equal to 1 over 1 minus e power plus j 2 omega p, not minus, a had minus. Okay. And following the same set of operations, you will get minus e power minus j omega p divided by 2j sine omega p. So, we have also obtained the coefficients. Okay. So, now we have the form 3, which is what we are working with. X e of j omega is given by the partial fraction expansion a divided by 1 minus r e power j omega p e power minus j omega plus b 1 minus r e power minus j omega p e power minus j omega. Okay. Last step, treat this as some a, treat this as some b. Okay. Then what do you get as the expression? A times a power n u of n plus b times b power n u of n, right. That is the corresponding x of n. Okay. Write down the expressions. We are through. This is equal to a times a power n will be r power n e power j omega p n, okay, times u of n plus b times r power n e power minus j omega p n u of n. Okay. For the final form, substitute values of a and b, whatever we have obtained as the expressions for a and b. Okay. So, what do we get? Those are nothing but constants. So, what you will get is r power n divided by 2j sine omega p. There is a e power j omega p in A, and there is a e power j omega p in the expression. So, what we will get is e power j omega p raised to the power n plus 1, okay, minus e power minus j omega p n plus 1 if you substitute from B, and do not forget to write down u of n. Last step, this expression is nothing but 2j sine omega p n plus 1. So, if you were to write the last step, this 2j and 2j will cancel, 2j will cancel. What you will get is r power n sine omega p n plus 1 divided by sine omega p. This is the sequence x of n which has got the DTFT given by x e of j omega. Okay? Now, why did we do this, this particular thing? We wanted to teach you about the factorization of polynomials. Second, wanted to make sure you know partial fraction expansion, how to get the coefficients of the partial fraction expansion A and B, how to compute that. Once you have it in this form, then the last step is only a trivial writing of a known result and simplification. So, how do we solve this this particular transform? The transform method we do is to take it step by step. Let me just repeat it one more time. This is the DFT transform pair number 7. Take the right hand side. The denominator is a second order polynomial. We factorize it into two first order polynomials with complex conjugate roots. Then we did the partial fraction expansion, obtain the coefficients of the partial fraction expansion A and B. Once you obtain it, the last step is to map it back into the corresponding time domain sequences. So, this is an important approach that I would like you to be familiar with. It also tells us that we have more or less been able to look at all of the properties of the Fourier transform pair. So, we can tick off the final two. We have got the Fourier transform of the unit step function, also that of the Fourier transform pair number 7. Okay. Now, some of the, we have covered all the essential results, all the basic techniques. It's now up to us to be able to apply a combination of these concepts in our study and in our analysis.